A tree is a graph that all the vertices are connected, but there are no circuits in the graph. A graph that is connected, but there are no circuits in the graph. I'll also give you a textbook definition. A connected graph where every edge is a bridge. And it probably works best for me to draw some pictures of this. So for some examples, I'll make up a graph here. Here is a graph of a tree with 4 vertices. Let's label them A, B, C, D. I can get from one vertex to another. I can get back, I have to repeat edges, but we're not talking about path or circuit here. We're talking about things like this. In the day of Joseph Kruskal, the telephone company wants to put out telephone lines, not quite like the cell towers and satellites we have here, although I imagine some of it dealt with some of that. Towers but want to make a telephone call from city A to city C. If I live in A, they can route my phone call through city B and then city C. And the person in city C that I'm talking to, their voice can come back, go through B and back to me in city A. So for something like this, I don't need a circuit. I just need a way for it to travel from one vertex to the other and then back again. In the case of something like a telephone call. On the computer, there are questions about, is this graph a tree? We'll look at a couple of these. Here's number 2 from the homework. Number 2, determine whether the graph is a tree. If the graph is not a tree, give a reason why. Well, that looks like the one I just drew. I did not intend that to be the case, but there it is. This is a tree. Number 3, determine whether the graph is a tree. If the graph is not a tree, give a reason why. There are 4 vertices. Vertex A and vertex D are disconnected, not a tree. The graph is not a tree because it is disconnected. Problem number 4. Determine whether this graph is a tree. Yes or no? Yes. As I look at problem number 4, I'm going to zoom in on that one. This is something I had warned you about previous. I had a student once taking a test, and she looked and looked and looked at the graph, do y'all see what I'm talking about? That edge that's between B and C, does it quite connect all the way to C? No. And because of that, she answered the opposite of what the computer's looking for. Your eyes probably go ahead and finish that connection, but maybe not always. So if something like that comes up, well, just kind of finish the connection there. See, when I zoomed out, it's hard to even see that. Look at number 5. Determine whether the graph is a tree. So this one right here, tree? No, not a tree because it has a circuit. This little, I can go C, E, D, C. Not a tree because it contains one or more circuits. Here's a fact about trees. I'm going to write it next to number 4. If a graph is a tree, it's going to have one less edge than the number of vertices. If a graph is a tree, then it has one less edge than the number of vertices. Now that by itself is not enough to say it's a tree. It has to be connected, no circuits, and all that stuff as well.